we'll be doing the relativistic formulation, or usually we call it as coherent formulation of electrodynamics. You can also see it as a four potential formulation of the electrodynamics. We'll be doing it. Okay. Now let's assume a charged particle. Okay. So if you are having a charged particle or a particle that's in an electromagnetic field. Okay, let's consider a particle and you put it in an electromagnetic field. Okay, it will interact with that field, is it? Okay, how it will interact with? By its charge, is it? Okay, so let's assume only the electric charge for the time being. So you are having some particle, so it's in some field. So let's say this is a region where you are having a field, and this particle will interact with the field. Okay, so this field can be due to the other charges as well, is it? Okay, so now if I have to describe the action of a particle, you know the action? You know action? No, action, you know? Okay, let me tell this. Suppose if you are in mechanics, if you are having a particle, it's moving along certain trajectory, you can assign for that particle along that given trajectory a quantity which is scalar in nature. We call that quantity as an action. Okay, and action is actually so it is defined through the Lagrangian instead of the Hamiltonian. Okay, so you can define it through Hamiltonian as well, but that's not a suitable definition. It's only defined through the Lagrangian. Okay, so this is how we define the action. Okay, let's say if you are having a particle moving from here to here, so it can go from this way, this way, this way, all the infinite possibilities, and for each trajectory you can actually assign an action. Okay, then for a true trajectory which is an extremum, okay, so this variation in action must be zero. That we call as an action principle. Okay, now let's say if you are having a particle that's in an electromagnetic field. Okay, this field can be due to some another source. Okay, got it? So how we can construct the action for for this kind of configuration, while you are having a particle, you are having an electromagnetic field, and you are also having an interaction between electromagnetic field and the particle. Okay, so how we can construct the action for this kind of configuration? Clear? So this is our question. Now, okay, how to do it? We can think this action consisting of certain parts. Like this way, we can consider, okay, let's forget about there is no field. Okay, when you are having no field at all, okay, so what remains there? Only the particle, is it? True? So I am assuming there is no field, so there remains only what? A particle. So you can consider, so you are having only particle here. Okay, so you can consider the action of this kind of configuration must consist of action of a free particle where there is no field, is it? Okay, when there is no particle, field is still there, is it? Okay, suppose if you are having no particle, so you are having a field, is it? So you can consider the action must consist of the okay, so it should be okay, you should be having an action for field itself. Okay, so what is remaining here now? Even both are present, is it? So that means the interaction part between the particle and the field, is it? So you can be having now, so the interaction part. So this is how we can construct the action of a particle in an electromagnetic field. Clear? Got my point? Now let's start. If we have no field at all, we have only the free particle. Okay, whether that is charged or not, let's consider only a particle of mass m. Okay, it's moving along certain world line. Okay, and we want to figure out its action. Okay, everybody followed it? Okay, good. So let's consider the action of a free particle in rather a relativistic free particle we will consider. Okay, let's consider its action. Let's go back to the non-relativist case. Tell me what is the action corresponding to the non-relativist case? Anybody? So it is half of mv square dt. Is that true? So this object is what? Lagrangian for a free particle. Clear? Now how you arrive at this kind of Lagrangian from first principles? Okay. So we start with an axiom. This Lagrangian is only function of q and q dot. Is it? Let me tell you. Okay. So we are having two functions. One function is defined in configuration space. That function we call as a Lagrangian. Okay. And another function that is defined in phase space. We call that as a Hamiltonian. Okay. Hamiltonian gives us the total energy of the system, but Lagrangian is simply an energy function instead of the total energy. Okay, it is simply the energy function. A simplest of the formula you have like this thing: mq dot square minus v of q. Is it? Is that true? Okay, so let's forget about this formula. Okay, let's consider free particle. So I want to construct its Lagrangian. A non-relativist free particle, and you try to construct its Lagrangian. Is it? How to do that? So Lagrangian must be the function of what? Q and q dot. Is it? Okay. So if I try to think of a free particle, so it's not bounded by any kind of potential. So we need to implement then the concept of homogeneity of space and time, as well as the isotropy of space. Is it? Is that true? So this Lagrangian can be actually the function of, let's say, for a free particle, it can be the function of, let's say, q. Okay, it can be the function of q dot. It can be function of, let's say, q dot square, and so on. All higher powers. Is it? It is simply the function. I need to construct what kind of function it is. Okay. So now, if I look at the isotropy of this space, what it says. Let's say Lagrangian depends on q, for example, but isotropy of space for a free particle, space is isotropic, is it? So when you think of the isotropy, all directions are equivalent, is it? So it means it should not depend on q dot. Q or q dot both, is it? Because all the directions cannot be equivalent then. I need all the directions to be equivalent, is it? So it should be only of the quadratic form. Clear? And for the free particle, what is the energy? Only the possible energy. What is that? It's kinetic in nature. There is no potential. So that means it should depend only on. It should be only the function of q dot. Is it? The first thing, if you apply, let's say, homogeneity of space and time, the direction, let's say, homogeneity of space time will give you what? All the points in space and time, they are equivalent. Is it? But if it depends on q dot, let's say on the velocity vector, so it will not be, at every point it will be different, is it? So it will violate the homogeneity of space and time, okay? And second thing is isotropy, all the directions are equivalent. So if it depends on, let's say, q dot, it will again violate the isotropy, is it? So that means it must be the, what? No, it should be the power of what? Q dot, is it? What is that power? It should be even power. Atisha, let's say if you are having this Lagrangian, simply it can be like the square of this thing, or let's say the fourth order, and so on, is it? It should be function of like this thing. Okay, why not this thing? Q dot square is a number. If I put let's say q dot cube, so it will be q dot square and q dot, is it? And this is actually direction dependent. So even odd powers will not appear. So only the even powers will appear. Okay. Now the point is here. Okay. You are having q dot 4 and all higher even powers. Okay. For a free particle, these will not appear. Why? Because I require actually an equation of motion for a free particle. What is constant? Acceleration. It is not acted upon by a force, is it? Or someone, I need a correct equation of motion for a free particle. Okay, that's why it must depend on only on what power? Q dot square. So the Lagrangian for a free particle, it is what? It is actually now proportional to Q dot square or velocity square. Got it? Clear? So now then you need to choose the constants. Okay. So those are actually half and q dot square. Okay, constants can be chosen from the equations of motion. Clear? Now let's consider the relativistic free particle. Okay, first thing, when you try to think of a relativistic case, think of Lorentz invariance. Invariance under Lorentz transformation. Whenever you think of some relativistic motion, try to think whether it is invariant under Lorentz transformation or not. Okay? We need to construct the action, and action is what? Look, action is a scalar quantity, is it? Is it a scalar function? That means when I transform from one coordinate system to the another coordinate system, what will happen? It will remain same. Is that true? So it means when I try to construct the action for a relativistic free particle, it must be what? Invariant under Lorentz transformation. Okay? Clear? So I need to figure out a function which is actually invariant under Lorentz transformation. Got it? Okay, second thing, it must be a differential of first order. This point is required because we need correct equations of motion. Okay? Clear? Got it? Okay. Now tell me, if you are having a free particle, let's say it is moving along certain trajectory or a whirl line, let's say you are having a free particle, relativistic free particle moving from point A to point B, okay, with a whirl line defined by x mu of tau. Okay. Now tell me, what is the quantity which is actually invariant, which I can construct from this x mu, or what is a quantity which I can construct for this particle moving along a trajectory, this kind of trajectory. What I am saying, okay, figure out a quantity which is an invariant quantity, or which is invariant under Lorentz transformation for a particle moving along this trajectory. Okay, what is a quantity which is invariant? Action. Forget about action. I mean, what is a quantity, a physical quantity which is invariant for this kind of trajectory? Or speed. Yes. No, that's not an invariant quantity. Oh, I am not considering any charged particle. I am just considering a particle. Simple, a particle of mass m. It may carry charge, it may not carry charge. Okay? What I am saying, okay, tell me, this particle is moving from, let's say, A to B. How I can consider this? So you are having, let's say you are having an event that has occurred here, okay? And let's say at a later time, let's think of an event happening here. So that's the particle started its journey. Okay, so now it has reached here. Then it will reach here. So what is a quantity that will be invariant under Lorentz transformation? I have given it. ds. Yes, great. Okay. So this ds is an objective which is invariant under what? So this is actually the proper time, is it? So ds by c gives you the proper time of the trajectory, is it? So that's only the invariant quantity under Lorentz transformation, which we can construct. If you are having a free particle moving, let's say, along a given trajectory, you are having only the quantity which remains invariant under Lorentz transformation, that is ds. And ds is given by, let's say, ds by c, that gives you what? This d term. Okay? So the proper time. Clear? Samashan? Okay, so that means, okay, and I require what? A differential of first order, it is this very quantity. This is a differential of first order. So I can write, let's say, action, okay, action for this very free particle, I can write it as proportional to, let's say, ds. Okay, when I am in, okay, I need to integrate it over the trajectory, is it? So let's say from point A to point B. So this is the world line. Clear? Now look here, this object ds. What was ds? So ds square is actually equal to c square dt square minus dx square minus dy square. So that is same as what? C square dt prime square minus dx prime square minus dy prime square minus dz prime square. So this is an invariant quantity. Okay? So I can write like this thing. Let me introduce minus some alpha. So this is proportionality. Okay, I am introducing alpha is a constant of sorry. So a constant we need to figure out from A to B ds. And minus sign is just to have, for this integral, to have an extremum. Okay, so there is no problem with that. I am choosing this alpha to be positive, this constant. So I am putting a minus sign to have, so that this very integral is having what? An extremum. Okay? Clear? Or a minimum value. So this is, what is unknown here? Tell me what is unknown. Alpha is unknown. We need to figure out alpha. So this is an action for what? A relativistic free particle. A particle of mass m moving at relativistic speeds. So its action is this very object. So let's write it, action. So it's minus alpha, let's say A to B. ds I can write how? Anybody? dt root of 1 minus v square by c square. Can I write it? Okay, what I have used? ds is equal to dt root of, there should be c, c should be there. This I can define like this thing, integral L dt. Okay, from point A to point B. So what is our Lagrangian therefore? Minus alpha c root of 1 minus v square by c square. This is the Lagrangian for a relativistic free particle. We need to figure out what this alpha is. Clear? So now how to construct this alpha? Or how to figure it out? So I will just take the non-relativist limit. Okay? Clear? Let's take the non-relativist limit. So what is non-relativist limit? So that's v by c is smaller than 1. Okay, that velocity of a particle is very small to c. Okay? So what will happen to this 1 minus? So you are having 1 okay, so L is equal to minus alpha c 1 minus v square by c square. This is equal, approximately equal to alpha c. So it is 1 minus v square by 2i c square. So it's minus alpha c plus alpha v square by 2i c. Is it clear? So it is simply a root, you take half here. So what is the Lagrangian for a non-relativistic particle, free particle? So you are having, so you have L is equal to half of mv square. Is it? Okay. So you are having, this is the quantity you are having at hand. So what is alpha therefore? So which gives me alpha is equal to mc. Is it? mc? Yes, alpha is equal to mc. So now if you put alpha equal to mc, what you will get? So mc square. So what is that equal to? That is the rest mass energy. So Samashama? Is that true? So you are having in non-relativist limit kinetic energy minus rest mass energy. तो समझ आओ? Okay. So this m is actually rest mass. Okay. So therefore I can have this Lagrangian to be equal to minus mc square root of 1 minus c square. So this is what? The Lagrangian for a free particle, a relativistic free particle. Now let's calculate, you can calculate other quantities as well. The canonical conjugate momentum, let's show you our conjugate momentum. Canonical conjugate momentum, P is equal to partial L by partial. Is that true? So how much is that? So you just differentiate it, it is minus mc square. So let me differentiate it for you people. 1 minus v square plus c square, and it will be minus twice. It's a vector v divided by c square. Why it has to be a vector here? Because this v square is actually v dot v, and I am differentiating with respect to, it is not actually with respect to vector, it's actually the ith component I am taking. It's like this thing. So you take ith component, that's partial L by partial vi. So what is that equal to? Minus m square partial by partial vi root of 1 minus, so let's write it as vj and vj, okay, by c square. Summation convention, so j, there is a sum, so it's simply v square. So now you differentiate it, so you will be having partial vi partial vj, so that will be delta ij, and that is I is equal to j, okay. So then you will be having vi, okay. So when you put it in the vector form, it will be like this, okay. So now let's calculate it. The two cases, so there will be actually two, so what is, so it is mv divided by root of 1 minus c square by c square. So this is the relative momentum, and similarly you can calculate now the energy. So total energy you can calculate. What is that? So let's write it as a Hamiltonian. So it is P, let's say P partial L by partial. Can you tell me? V. So it is P dot. So it's a dot product here. Okay, minus L. So what is that equal to? P is how much? So you can get it mc square divided by 1 minus c. So this is the relative energy of it. So total energy of a free particle. These things you know. Okay, you can now calculate. Now this very quantity is very important. So you are in P is equal to epsilon V by C. So this is actually the total energy. Okay, so I have put actually, so let me write it as epsilon and this. So this is the total energy. So you need to just divide P by this object, you will get actually V by C square. So this is an important identity. Similarly, you can show that. So the energy, so that's equal to root of P square C square plus M square C raised to 4. Okay? Clear? Yes? Okay, so this is, we have, okay, arrived at the Lagrangian. From the Lagrangian, we have calculated all these quantities. Okay? Now let's start doing the action principle. Let's arrive these quantities through the action principle. So let's take, you are having this action as minus mc, what it is? Mc integral from a to b dx. So this is our action. Is it? Clear? Now what is this ds? Anybody? So it's, okay, ds is root of dx mu dx mu. Is that true? So ds square is that. Okay, so what is the variational principle? Or action principle, what you call it? Okay, so there exists an extremum path for which this delta x is equal to 0. So how it is arrived at? So you can look at, let's say you take a trajectory, you have a point, let's say point A to point B. So there can be many possibilities. Let's say So these are the possibilities. I have taken only 3. Okay, what you do in this variational principle, you assume a given path is what? It's a true path. Okay, so let's assume this is the true path. From that true path, you vary actually. You vary your coordinate. Once you vary the coordinate, what will happen to the action? It will change, is it? So you will be having action a different kind of trajectory, like this thing, or you can be having this kind of trajectory. Okay, so this can be new thing or this can be new thing. So suppose if I am assuming this as a true path, what should be then the variation of action? 0, because it is so once you try to vary it, it will come back to the same trajectory, is it? So we are varying it actually in the neighborhood of that very path. So that is actually this variation in S is equal to 0. Got it? So in other words, you do this way, you are having large number of trajectories from point A to point B. For each path you assign an action, is it? And you try to figure out what is the true path. Okay? For that true path, this variation should be 0. You can consider all other paths as the variation to the original path. Okay? Clear? Got it? Okay, so in our assumption, what we will be doing, we are keeping these endpoints fixed. Okay? So I am just doing endpoints of the trajectories to be fixed. Okay? So I am not varying any endpoints. There is a possibility where you can change these endpoints. Okay, you can be having a situation where you don't keep these endpoints fixed. What does that mean? Suppose if you start from a trajectory, let's say point A to point B, and you vary it to some another path. Okay, so the endpoints get what? So endpoints are not fixed now. So they have changed because I have changed the trajectory, is it? So that means I have actually translated trajectory to a new point. So got it? So this is a different situation than this kind of situation. Okay. So we'll be doing this kind of situation. Okay. So let's vary then. So from here, so I am having, so this delta S is equal to minus MC integral variation of this ds. Okay? Clear? So what is that equal to? Minus MC integral. What is this variation in delta S? Okay, so let me calculate it separately. So you are having this ds here. Okay? So let me calculate this separately for you people. So it is ds. So what it will be? It will be simply the variation. So it is simply the differentiation you can take. Okay, here you have to apply the differentiation rule. So it's 1 divided by 2s root of dx mu. Okay, then variation of, so you do the differentiation inside. Like this. Clear? So what this object is? 1 by 2s ds. So you can write it like this way. So it is dx mu, variation in, so product rule you follow. Okay, plus then you are having variation in this dx mu. Clear? Okay, now if you see, these are both the same terms, is it? So you can lower down this very index and raise it simultaneously. So this term I can write like this thing, delta dx mu and dx mu. So if you are having a contract index, so that means one is upper and one is lower, is it? So you can interchange the two. So let's say you are having an upper index here and lower index here, both are contracted, is it? So you can, what you can do, you can raise this up and you raise this simultaneously. Sorry, you lower down this simultaneously. Okay? Clear? So that means these two terms are same. So it means it is twice and 2 will go. Okay, let me write 1 by 2s ds, 2 times dx mu delta dx. So now look here. So in this very object, I can actually interchange this delta and d. You got my point? So these are linear derivatives. So I can interchange the two. So I am having this object now, dx mu by ds dr delta. Clear? So here I have interchanged it. So now what this object is, can anyone tell me? So it's a velocity 4 vector. Last time we have done it. So it is a velocity 4 vector. Clear? So let's write it here. So what I am having from this very variation, so therefore I am having this variation in S. So that's equal to minus MC integral, let's say from point A to point B, our time from starting point to the final point. So it gives me U mu dr delta x. Clear? So much our? Everybody followed it? So now what is that equal to? Let's integrate it by parts. Why I need to integrate this by parts? Look here, so you are having a variation of x within where? In the derivative. So this dx mu is not an independent differential. It's actually delta x mu. So if you look at the trajectory, at any point you are actually independently varying the path, the coordinate. So that's why you take these objects to be linearly independent. Clear? So you need to actually free this very object from this d. Okay? So that's why I need to do a integration by parts. Now let's integrate by parts, keeping this as the first object and this one second object. Now tell me, what is the trajectory? Okay, what is the measure of integration here? So it is ds, is it? So I am going along the trajectory which is defined by ds. Okay, so I am integrating it through ds. Okay, so let's write it. So it is u mu, so it will be simply delta x mu, and that's evaluated at what? Let's say point A and point B minus an integration from point A to point B, then it will be du mu by ds and delta x mu. Is that clear? And this variation delta s, that's actually equal to 0. Clear? Okay. So now look at this very object. This object is equal to 0. Is that true? Because I am keeping n points fixed. Okay. So n points are fixed. So what I am having? So this delta x at point B, that is 0, and delta x at point A, that's actually equal to 0. So much, Evan? So now this object is equal to 0. What remains there? This object. Since this is a linearly independent term, okay, so they are non-zero things. What that means? So when I am saying this variation in S is equal to 0, so it means this object has to be equal to 0. So which gives me, but it is multiplied by what? M minus times MC. So I am having MC dx mu, sorry, du mu by ds, that's equal to 0. Can anyone okay, so this is the Newton's equation, okay, in 4-dimensional form for a free particle, relativistic free particle. Now u mu, so what it gives me? It gives me the constant speed, is it? U is the velocity, is it? Du by ds gives me the acceleration. For a free particle, it is unaccelerated, is it? So there is no acceleration. It is a uniform motion. Huh? Got it? Okay. Okay, so now that before moving ahead, now what I will do, so I arrived at the behavior of a free particle, how it looks like in 4-dimensional form. It is unaccelerated completely, so there is no force acting on it. Okay, and this velocity is what? What is velocity here? So it's a constant of motion. So that means it will move with a constant velocity, okay, in 4 dimensions. Now let's do this case. Okay, let's fix only one endpoint. Endpoint, say A. Okay, so that means variation of x at point A, let's write x mu, that's equal to 0, and variation of x mu at point B is not equal to 0. So what I am doing? I'm just keeping one point fixed, is it? You can keep actually both points, sorry, you can keep both points varying. Okay, there is no problem. You can keep both points varying. Okay, let's fix both endpoints. No. Let's assume endpoints are varying, like this thing. Endpoints are varying, not fixed. Okay, but the trajectory or the world line satisfies Euler Lagrange equation. Euler Lagrange equation. That means equation of motion. So that means the trajectory, what I am taking. So I am having this kind of, let's say, the trajectory. Okay, so you are having from point A to point B. I am assuming this trajectory satisfies what? Equation of motion. So what is that equal to? MC du mu by ds, that is equal to 0. So my first assumption is I am taking a true trajectory now. Okay, it means it satisfies equation of motion. But what I am trying to do, I am just moving these endpoints to some another point. Samajh? Clear? So now endpoints are not fixed; they are varying points. Okay, the variation at these endpoints is not equal to 0. So that means delta x at point A is not equal to 0. Clear? So now let's go to this equation. Okay? So I have not, okay, I am only saying it satisfies equation of motion. Okay? So there is no, the variation in action is not 0. So here, so we are having now variation in action. So variation in action, now let's write it. How we have calculated, it's MC u mu, okay, delta x mu, okay, evaluated at point A and B minus integral A to B. So it's like this thing, okay, du mu by ds. Okay, so you are having delta x mu. Okay, so now this object is 0, is it? By assumption, this is what? So this object is 0. Is that true? By assumption, we have assumed this object to be 0. We are not assuming delta x to be 0, is it? So we are just assuming equations of motion are being followed. So what you get? So you get simply minus mc u mu delta x mu evaluated at point B minus delta x mu evaluated at point A. Is that true? So just I have evaluated this delta x at the endpoints. Okay, since this is non-zero, this is also non-zero. Is it clear? Okay, so I can define this object to be, let's define this object delta x mu. So a finite variation, because, so this will give me a finite number, is it? So let's call that finite number to be delta x mu. Clear? Everybody is following it? Okay. So what I am having, so this delta s therefore is equal to minus mc u mu delta x. So from this object I can now calculate a quantity. Okay, so let's calculate a quantity partial s by partial x mu. Okay, let me write. Let's write x mu. So so what is that equal to? Minus mc u mu. Simply, you are differentiating this with respect to this. So samajh clear? Samajh? So you are having this very object at hand. So this derivative gives me a 4 vector. U mu is a 4 vector, is it? But it's multiplied by some quantity, what we call mc. Samajh? Clear? Till this point it is okay? Okay, good. So is it mc or mc square? Huh? That should be mc square probably. Huh? What? Why it should be mc square? MC, no, there is no. It's okay. So we call this object as energy momentum, like this. Okay. So this is a 4 momentum vector. 4. Now tell me, if I am having a 4 vector, what does it mean? If I am having a 4 vector, what does it mean? So its components transform in the same way as X transforms under Lorentz transformation. Is that true? So this defines me a 4 vector. Okay, now let's check it. Let's take, okay, you know it from here. Let me tell you. Okay, first let's write the components. Let's write P is 0. Okay? Let's try to understand what P0 is. Okay, so what is P0? Minus MC U0. Okay? 0 component of the velocity. So what is that equal to? Sorry. I need to define it by 4 vector. We define it a minus sign here, so it will be plus. Okay? So this object is okay. There is no problem with this. I have defined my 4 vector P mu as minus times this derivative. Clear? So now tell me, what is this U0? It's 1 divided by root of 1 minus V square by C square. We have done it in the last lecture. Clear? Okay, so can I write it as 1 by C times MC square divided by root of 1 minus V square by? Can I write it? So what is this quantity? It's energy. Clear? MC square by root of 1 minus V square by C square is the energy of the particle. So therefore I can write this P0 as, let's say, energy by C. So that means 0 component of this P gives me what? Energy of the particle. Clear? Now let's write Pi, ith component. So let's write I. So I is 1, 2, 3. So let's write it. So it is MC Ui. So can you tell me what is Ui? So it's actually ith component of the velocity, 3 velocity, divided by C times root of 1 minus V square by C square. What is that equal to? M Vi divided by root of 1 minus V square by. Now tell me, what is mv by root of 1 minus V square by C square? It is the momentum, rather the 3 momentum. It is the momentum vector. So, or I can write, I am having this momentum vector to be mv divided by root of 1 minus V square by C square. So that means I am having a 4 vector P mu. Okay, so this 4 vector P mu I am having like this thing. So the 0 component or the temporal component gives me the energy, and the others give me what? The 3 momentum that I will represent by vectors. So it's E by C, so it's Px, Py, and C. Clear? Okay? समझ आओ बेटा? हाँ? So now let's look at this very formula. Forget about this thing, let's look at this derivative. Everybody followed it, what I have done? So we have calculated a 4 momentum vector for a free particle, is it? So let's do something more. So if I have to write now its covariant part. So P mu, how I will write it? G mu nu and P nu. Can I write it? So Samushima, now let's write that. So it will be, when I am writing G mu nu, so the temporal component will be same, but only sign change will be for special component, is it? So it's minus. Samujha? Got it? So this we have been doing. Okay, so now let's write the magnitude of this 4 vector. So P mu, P mu. So that is same as what? P mu, P mu. So what is that equal to? Now multiply the components. So it's E square by C square. E by C, and then P multiplied. So it's P dot. So what is that equal to? So it is E square by C square minus P square. So what is that equal to? Can you tell me? So it's like this thing. E square minus C square P square divided by C square. What this object is? M square C raised to 4. What is E square? C square P square plus M square C raised to 4. So this will be simply equal to M square C raised to 4 divided by C square, that is M square C square. So it means this object is what? P mu, that is simply equal to M square C square. So much on? So now look here. So it's what is MC? It's a scalar quantity. M is the rest mass, C is the velocity of light. Both are what? Scalars. M square C square is what? An invariant quantity under Lorentz transformation. It means this object is what? Invariant under Lorentz. It is a scalar quantity. Huh? So much on? Clear? So that means your energy momentum relation. So this E square is equal to P square C square plus M square C raised to 4. In 4-dimensional form, we put it this way. Clear? So this is its representation in 4-dimensional form. Okay? Now let's look at this very formula. Okay. So I am having this very object minus partial S by partial X mu. Let's look at these things you have already done in your mechanics course. So now let's take mu is equal to 0. So what it gives me? Minus partial S by partial X0. So what is that equal to? Minus partial S by C partial T. Because X0 is CT. Is it? Is that true? So it's 1 by C. What is this minus partial S by partial T? So what this object is? If you are differentiating partially the action with respect to time, what it gives me? Hamiltonian. Is it? So that is energy. So this object is what? Hamiltonian of the system. That's actually the energy. So it is simply E by C. Clear? So this is the Hamiltonian. Huh? So now if I take mu is equal to I, that means ith component. 1, 2, 3. Okay, so what it gives me? Minus partial S by partial Xi. So what this object is? It's simply the momentum. It is simply what it gives me. It is simply the gradient of S. What is gradient of S? It is momentum. Is it? So that's why if you see from this very formula, so I'm having 0 component as energy and the special component says momentum of the particle. Clear? Everybody followed it? Okay, so this is all for this relativistic free particle. Now let's go to Mr. Field. Rather, let's go to if we are having a charged particle. Now let's consider the interaction between yes. Okay. So we still have some time. Huh? Okay, you want to relax for 5 minutes? Just relax. In the meantime, fetch me some water. So when you are having an interaction between particle and so this is the second case. So we started with a free particle. Now it's in the electromagnetic field. So the first part of the action, what we have done? We have cleared that, only the free particle. Now the second part would be what? An interaction between the particle and the field. And the third part will be only the field, is it? So that means without the particle. Clear? So we'll be considering this interaction between the particle and EM field. Clear? Okay, now how to construct the action for that? Okay, there should be a guiding principle to arrive at the action. Is it? So first thing, okay, do you know what a field means? Physically, okay, think physically instead of mathematical definition. Mathematical definitions are quite a bit complicated. Huh? Physically, what a field means?
Some scalar quantity is a constant horizontal.
That's okay to a certain extent. Simple definition of field. I will assume that definition only. So you can consider it as a region, is it? a region in space time, okay? At every point of which you define a given quantity uniquely. Let's say if you are having a scalar field, you consider a region in a space time. At each point, you are having a scalar quantity defined, okay? Uniquely rather. Samajh? Now, if you are having at each point a vector quantity defined uniquely, you call it as a vector field. Clear? Think of the temperature. Okay, let's say you move around. Let's say in this very room, at every point you will figure out different temperature. Is it? Rather, the gradient of the temperature will be different at different points. Is it? You can consider that as a temperature scalar field. Sorry, that's a vector field. It's a gradient. Is it? So it's the gradient of temperature that will be a vector field, and the value of gradient at every point will be unique. You cannot be having two values of gradient at a given point. Is it? So much. Or think of an electric field. Let's say if you are having a point charge, around that you are having certain region where you can experience force of attraction or repulsion between test charge and a given charge. Is it? So you can draw all these things, the vectors at each point. Is it? So much. So at every point you are having a unique vector that describes you the field. Is it? So you call that vector as an electric field. The length of the vector at that very point will give you what? Magnitude of the field, and the direction of the vector you will give the direction of the field, because the direction of vector will be the direction through which or along which the test charge is moving. Clear? Similarly, if you define at every point uniquely a tensorial quantity, that will give you a tensor field. Is it? So this is the simplest of the definitions of this concept of a field. Okay. So more mathematically, we have to define different manifolds, and on manifolds you are having certain properties. They describe it, but I will not go into that. Okay. Now, how to since we are dealing with an electromagnetic field, how to describe the electromagnetic field? So EM field. So usually we in terms of the vectors. Okay, so how we describe the electric field? By electric field vector, is it? How we describe the magnetic field? By magnetic field vector. You define these. Let's say you are having certain region. At this point, you describe, let's say, some arrow. Okay, you will be having an arrow. Let's say, let's put a uniform field, okay, like this way, and these arrows will describe what? Let's assume field E. Okay, and you can be having the magnetic field vectors. But similarly, let's say you are having current carrying conductor, and the direction will be what? So B. Is it? So this is how you define the electromagnetic field. If you are having an electromagnetic wave, okay, so which consists of both electric and magnetic fields, they will be perpendicular to each other by those vectors you describe by E and B. Okay. Now, how many quantities we are having here? So to describe an electromagnetic field, so we are having 6 quantities, is it? So this is having 3 components, this is having 3 components, is it? So it's vector in nature. To simplify our calculations, instead of doing in terms of these vectors, we introduce actually this. Instead of doing in terms of these physical fields, these are physical, what you measure actually, we do it in terms of the potentials. Okay, so there is a reason. Okay, the first reason for that, doing electrodynamics or any kind of theory in terms of the potentials, the first thing is it's simpler to solve in terms of potentials than in terms of E and B. Okay. Second point, it is simply the second point, to a certain extent that's also true. Let me tell you, how many Maxwell's equations you are having? You are having 4 Maxwell's equations. 2 are scalar in nature. One is del dot E, another is del dot B, is it? So how many components there will be? So there are only 2 equations, is it? Del dot E is 1 and del dot B is 1. So 2 equations. Others are actually vector equations. How many are they? So there are 6. In total, how many equations you are having? But how many quantities you are having? 6 quantities. So you are having, these are actually vector quantities, is it? So E is having 3 components, B is having 3 components. Maxwell's equations are vector equation, is it? Two scalar equation and two vector equations. So total are 8 in number, but you are having only how many quantities? So what? So you are having number of unknowns are less than the number of equations. So how many solutions are there? Huh? So there can be many possibilities, is it? So there should be the many possibilities, rather infinite number of solutions should be there, is it? So, to satisfy the given set of equations, is it? So, but in electrodynamics, or in electrodynamics, what we choose certain kind of conditions on the fields. Okay, if I choose, let's say, two constants, two conditions, because my number of variables are only 6, equations are how many? 8. If I choose now, let's say, two conditions, so how many equation and variable will be there? 6, is it? So you are having 8 equations, okay? So if I choose two conditions, they will yield me, okay, certain set of constants, is it? Constants, okay? So I will be getting, let's say, the number of variables and the number of equations will be same, is it? By choosing those kind of conditions. And if I choose those conditions in terms of A and B, actually, they are difficult to choose. Okay? So they become difficult to, the calculations become very tedious. Samashaman? Okay. Now if I choose them in terms of the potentials, look, if I choose, how many potentials I can choose for E? Two potentials, is it? One is scalar potential, another is vector potential. E can be written in terms of phi as well as A, is it? But B can be only chosen in terms of A, is it? How many components do you have? 4. So I can convert actually Maxwell's equations to a certain form, okay, in terms of these phi's and A's. And the conditions which I am choosing, okay, they are actually, we can choose them in terms of this phi and A in a simpler way. It's very flexible to choose those conditions in terms of phi and A. So that my number of equations and my number of unknowns become same. Look here, okay, I will give you this way example. So you observe the light. How many degrees of freedom light is having? 2 degrees of freedom, is it? So you are having 2 degrees of freedom here means the polarization states, is it? So for light, the degrees of freedom is simply polarization. How many are there? So you are only two polarization, either up or down, or left or right, or elliptical left or elliptical right, is it? So these are only 2 degrees of freedom. Got it? So these are physical degrees of freedom. How many variables you are having? You are having 6. So you need only how much? So when you are having 2 degrees of freedom, you need only 2 variables to describe them, is it? So in terms of potentials, it becomes actually simpler. So these are 4 quantities. If I choose 2 constant conditions on these 4 numbers, how many remaining will be there? 2. So that will give me the simpler, I mean these 2 degrees of freedom. Samajh? So this is an argument why we require actually the potential formulation of the electrodynamics, or potential formulation of any kind of theory. So Samajh, it makes our life simple. Nothing more than that. Okay? Clear? So once you do in terms of potentials, you will actually feel. So why we are doing these kind of things. Okay? So there is a kind of condition what we call as a gauge condition. I will tell you that. So that helps. That's beautifully put in terms of. I mean, these phi's. Okay? So we will see those things step by step. You will actually come to know why we require why it is easier to handle these phi and A instead of that E and B. Samajh aaya? Clear? Shall I proceed? Now what is our problem? Our problem is not this thing. What is our problem? Interaction between particle and field. Okay, how to describe that? First, I require what is a variable that describes field, is it? So I require that. For that, I will introduce a vector which will describe the field. Okay, so my field, okay, EM field, I describe by this 4 potential, for which the temporal component is simply phi and vector potential represents the scalar potential. Let's forget about this 4 potential. Okay? What is the property of a particle that helps it to interact with the EM field? It is charge, is it? Okay, now how I can represent the interaction between a charge and the field? It is the interaction energy, is it? Energy means, okay, if you are having a particle interacting with the field, you just calculate how much energy it requires, okay, to get interacted, or how much energy it releases once it interacts. So you need to calculate the energy. So tell me how much energy. So let's say you are having only the scalar potential phi at hand and charge is E. Let's think a particle of charge E. Phi represents now electromagnetic field, is it? Or let's think only the electrostatic field. We will not consider the magnetic field. So how much energy is there if you are having charge E? So this phi is it is the field produced by some another charge, is it? So this is a particle what we are considering in that field, is it? So much even? Now tell me how much electrostatic energy will be there? Phi. Now I go. E times phi is what? Charge multiplied by potential gives you what? Energy, is it? Or the potential energy in the field, is it? So much even? So this will be the, if you are having only purely electrostatic field, so this will be what? Electrostatic energy of a particle in the field of phi. You sure? Okay, now if you are having purely magnetic field A and you are having charge E, if you are having purely magnetic field, that is described by the vector potential A, is it? So now tell me how much energy is there. Okay, if this your charge is in the electromagnetic potential, sorry, in this vector potential, how much energy is there? So how we calculate the energy of a particle in the magnetic field? You just see at what velocity the particle is going, is it? So the static particles have no magnetic field energy, is it? Because it does not generate magnetic field, is it? So what you need? A moving particle, okay? So moving particle is having a velocity. Now let's say velocity is v, okay? I will give the hint. So v is the velocity. Now tell me how much energy is there? Huh? One second, beta. Any idea? You? Oh, no, energy. Simple in terms of EV and A. Just tell me, what is the energy? Yes? What is, how I can calculate the energy? What is E times V? You are having a particle moving with velocity, it is having charge. What it will generate? What it will have? How you can think? It is a current, is it? Isn't it? A charge moving with certain velocity means it is a current, is it? So current multiplied by vector potential gives you what? Energy. Magnetic energy. Simply magnetostatic energy. So tell me now, how much is it? So it will be simply E A dot V. Is it? Got it? So now we have figured out in our electrostatics or magnetostatics what is the energy, is it? So this will be simple. E phi will be the interaction energy in electrostatic field and A dot V will be what? Energy or the interaction energy in magnetostatic field, is it? Samajh? Okay, since we are now in the 4-dimensional form, okay, so what will be the energy? Munir sir. So I am moving now along the trajectory. Let's say, so let's say you are having a trajectory from A to B. So now you are having a charge at hand E, is it? So much on? Now tell me how I can calculate the interaction energy. This particle, what is in the background? In the background is field, is it? So let's write this as field. So this is the background. Okay? it's in this field, okay? Rather it's in this field, this way. What I can do now, let me take a small line segment here, okay? Let's consider this very line segment. How much charge is there? Yes. Yes. This trajectory is defined by x mu tau. So what will be the small line element? Dx mu tau. So what is the charge? So this is the amount of charge in this very element, is it? So much amount? Clear? So what is, how field is represented? Now tell me. So field is represented by A mu. Tisha? So how I can represent now the interaction between this element and this field? Simply you multiply this object with this. So now look here, what we have done? E multiplied by 5 and V multiplied by A. Tisha? So what would be the interaction here? So it will be, so the interaction energy will be simply equal to E d, okay, let's write dx mu E mu. Tisha? Is this? So calculate small this. Let's take mu is equal to 0. So what this dx mu is? C dt. Tisha? Okay, so you are having simply E times A0 is 5. Tisha? So now A0 5. So that means E times 5 is the energy. So much ever? Rather, I should not say interaction energy. I should say it is the. Okay, let me put this way. So let's write this. Okay, I should not. This is not the interaction energy. It gives actually with the infinitesimal action at this very point. Okay, okay. Let me tell you. So I will write now the action along this thing. Some minus times. Minus I am choosing simply what? To have the extremum value of the part of this integral. Some a to b. Let's write dx mu a mu like this. So that this should be actually, this should give me the Lagrangian, is it? Samajh aaya? Okay, now let's take 0 component only, then you can understand it. Take the 0 component. You take x0 and a0. So if I take 0, so it is dx0 a0. What is dx0? C dt. What is a0? Phi, is it? So it is actually in the integral like this way. Okay, e by c integral c dt phi, is it? So c and c cancels. What remains there? E phi and dt. So what this is? Interaction energy. Tisha? So because Lagrangian represents the energy, so E phi is the energy of a particle in the static field, static electric field. Is it clear? Is it clear or not? Similarly, now let's take xi. Let's take ith component. So it will be, let's take E by c. Ith component will be what? So it will be simply dx vector. What is a mu? So it will be actually, let's write simply as dot vector a for important sign. So dx I can write as v dt. Yeah? So it is v dt dot a. Okay, so what it gives me? V dot a dt. Okay, and there is a this e by c. So you are having e times v dot a. E times v dot a. That gives you what? Magnetostatic energy. Clear? So that means that if you are having a charged particle moving okay along certain world line, okay, in a given electromagnetic field represented by this a mu, its action, the action corresponding to only the interaction part will be like this thing. This very object integrated along the world line. Samushaman, E by c is a constant to match the dimensions. Okay, minus sign is to have for this integral to have what? The minimum value. Clear? Samushaman, because c is a positive number, E is a positive number. If E happens to be, let's say, a negative number, then you don't need to choose what? I am taking E to be the magnitude of the charge. It's always positive, okay? So let's write that. Okay, so what is our action? Yeah. So I will put it as I. Interaction means SI means interaction, so it's minus E by C integral. Let's write this way. A mu dx. Any question? Hello, any question? Okay, good. Now let's write it carefully. So it's minus E by C. So I will put as A0 dx0 plus AI dx like this thing. So there is a sum over I, sum over I. Okay, so if I have defined my field in this way, so its covariant part will be simply phi minus E. Clear? So what is that equal to? Minus E by C. What is A0? It's phi dx0 is C dt. Okay, what is AI? It's minus A. So it is A dx, so it will be simply vector dx like this way. Clear? Okay, so that's equal to minus E by C integral C phi dt minus A. So dx, I can write three velocity vector V as dx by dt, so that this I can write V dt. So now take V dt out, so take this inside, so it is something minus, okay, let me write this way, minus E by C, okay, sorry, okay, let me write this first, so it is E by C A dot V minus E phi dt. So this is equal to the Lagrangian, so let's call this as Lagrangian I corresponding to the interaction. So therefore I am having this. So what it gives me, this is the magnetic field energy, because you are having the particles and the kinetic energy, is it? So that's why you are having a positive sign here. So you think this as a particle in certain potential, scalar potential. Potential comes in with a negative sign, is it? So now let's calculate, let's write the total Lagrangian, I mean total action. So this is la end pointer, total action without field. So that means you are having particle plus its interaction with field. So what is that? So S is equal to, so minus MC root of MC square. Is it MC or MC square? 1 minus V square by C square. Okay, then plus E by C, E dot V minus E. So this is now the Lagrangian. Clear? So let's stop here.
Sir, if there is no field, then interaction is.
So this is interaction of the particle. V is the velocity of the particle, of this particle, is it? So it's interacting with the electromagnetic field. A is the electromagnetic field.
Which is without.
Without field, is it? So I mean here, okay, sorry. So we are considering total action of a particle and interaction with its field. We are not considering the action for the field itself. So there are three terms. So the first term is the action only for the particle. Another is the action only for the field. The third term is action for the particle interacting with the field. I am not considering the field. So much for action, separate action for the field, is it? You got my point? I am only considering there exists a certain field with which the particle is interacting. Okay?